Okay, so we're very happy that Smarajit is here.
Finally.
Introduction, of course. And so he'll be telling us about some interesting new things on dynamics of supercooled liquids. So it will be about 1 hour.
I cannot spill over.
Extended to 1.25 with questions.
1.25 quick question. Okay. Yeah, good morning, and let's start. I hope that there will be some other people who will join in this. So my talk will be primarily on something called something like order in a disordered systems, and I will explain what order is. So this is so there is a new term which is called amorphous order. But now if you ask me what is it, can you visualize it? That's difficult. But we know there are methods to compute it, and I'm going to discuss some of that. And then I will come to another situation where there are explicit order, like there will be crystalline order or some sort of structural motifs which are growing in size, and how those order controls or plays an important role in dynamics of supercooled liquid. Okay, let's say one more. Yeah, and I think I'm also one of the organizers, so I should not thank myself in principle, but I should thank other organizers for managing it for this 2.5 months or something. Let's start. I think some of you know about glasses, but there are few who are not familiar with glassy liquids. So let me quickly tell you, if you take any liquid, and so liquid has this tendency that if you go to lower temperature, then they start to become, there is a tendency to crystallization, but you can bypass it but by doing a rapid cooling. So if you cool it very fast, then you can go into a state which is disordered, and and that state we call supercooled liquid. And you can also, you know, if you heat it very fast, you can also go to a superheated state. So we will be concentrating on supercooled state, and so there are many interesting phenomena which happens once you go into supercooled liquid. So one important phenomena is that in this supercooled temperature regime, if you change temperature by, let's say, order of 50 to 100 degree, the relaxation time can change from order 1 to 10 to the power 13, 14, which is a huge change. So this is what has been shown here. So you see this is in log scale viscosity into some -4 to something like 13, which is even more actually. So it's 10 to the power 17. And okay, so let me. But then if you look at the structural quantities, so here I plotted 2-point correlation function, the radial correlation function, and that doesn't show much change. So there are two curves, the red and the dotted blue curve. So there are some changes, but they are not very significant. To explain why the relaxation time even between these two state points are so different. So let's, for example, let's say for temperature which is T equal to 1 in a reduced unit, the relaxation time is order of 1 or maybe something like 5, again in the reduced unit. But then once you go to this temperature T equal to 0.45, it is already 10 to the power 4 almost. And sometimes it, at least for a different model system, it can be even higher. So you see that with a very small change in temperature, the relaxation time changes very drastically, and you don't see much structural changes. So there is one more other interesting feature is that there are few liquid which show that change in viscosity with temperature in a very different way. Some show this straight line, so which will mean that viscosity goes as e to the power some constant by t. So this is called Arrhenius law, and then there are few which are which changes in a very non-Arrhenius way. That's a super Arrhenius behavior, and so there are terms for these two types of liquids. So those who fall in this straight line are called strong liquid, and those who are within this, those liquid for whom the viscosity changes in a non-Arrhenius way are called fragile liquids. And there are a lot of efforts to understand why certain, yes. Yes. So there are certain structural changes. So for example, like this split in the peak can be understood. So there are this kind of structural motif which appears. you have spherical particles, then this kind of structures are becoming more abundant, and also you have this structure for 3 particles, okay, and and these 2 peak will be related to this and that. And for the liquid, the amount of or the concentration of this such structural motifs are not that much. So that's why it's not splitted. So there are structural changes. I'm not saying, I'm not ignoring it completely. There must be something happening, right? Otherwise, why there is so much of change in viscosity? Yes, you don't see this split in the peak. Okay, so there are finer details. So I'm not going into all of those, but if you have questions, we can discuss later. So there are a lot of effort to understand why certain liquids are strong and why certain liquids are fragile. So understanding fragility is a very big question also, and is there a unified way to understand it? So when I talk about glasses, so what are those? Are there any, do they exist in this world? Yes, they exist. And there are these metallic glasses which have been used everywhere, including your phones. And there are very interesting properties which has been exploited, and there are many devices which are made out of this. And there are also these foams, emulsions, they all fall into the same category. And there are a lot of effort in colloidal systems, which in these systems you can do microscopic experiment. So you can look at their dynamics. It is more like an analog of what we do it in computer. So this is computer simulation results, and these are all like you can do experiment and visualize each colloid and how they move and try to understand similar physics. And so you see there are, these are all computer generated structures of glasses, and you probably also you can clearly see there are certain changes, right? So the structures are somewhat different. And the second part of my talk will be focusing on this, okay? Okay, so let me tell you quickly. So as I said that the relaxation time increases very rapidly, and there is not much change in the structural quantity what we can calculate using, let's say, the pair correlation function. Then some of us, including Chandan and Srikanth, and also there are other people, and we also made significant, I think significant contribution on this. We asked whether there is a growing length scale, and what will be the methods to calculate them. And we'll also show that that there are probably 2 types of scale. One is static length scale, and the other one is a dynamic length scale. And okay, so this goes back to my PhD days in 2009. So that time we did a lot of analysis on 4-point correlation functions instead of 2-point, and we did a very detailed finite size scaling to show that there indeed exists growing static dynamic length scale. Initially, at that point, we were not very sure whether that length scale also controlled the time scale or the viscosity. But later part of, once we finished this work, we realized that the length scale we calculated via 4-point susceptibility is not related to the viscosity or time or the time scale. So then we started to look for a different type of length scale, and those I'm going to discuss more. So about this full clumsy slide, if you have more questions, we should discuss later. Otherwise, like the whole talk will be on this. Okay, so let me come to the static length scale, which is the focus of this talk. And so this static length scale is related to something called amorphous order. So now there is nobody knows how to see it, but there are ways to compute this structural order, if you believe what this order is. And there are one of the famous method is called point to set correlation function. I will come to that again later. And there is also something called patch repetition length scale. Again, this is if you want to really know in details, you have to spend a lot of time. And then we also proposed something which, by looking at the landscape and the curvature of individual minimum in the landscape, and connected to that, the curvature seems to be connected to the length scale which I am talking about. And also one can do scaling analysis of relaxation time or viscosity to find out those length scale. But all of these methods are somewhat, they are very expensive in terms of computation, but and apart from that, it's not straightforward to do it in experiment. You can do it in colloids, that's for sure, but for let's say other liquid like glycerol or all other glass forming liquid, you cannot do any of this analysis. So then these methods, though they are useful to give us insight about glasses, they are not very useful for practical glass forming liquids, and if you want to understand them, then it's not that useful. So we have written in with Chandan and Srikanth to review on this length scales in glasses. So if you are interested, you can have a look at it. So let me now come to this experimental effort to calculate this static length scale, and this is very recent one, which is from this group which has all sorts of big names. And huh? Okay, yeah. So he has more information on this. But so the whole point of this is that one needs to calculate fifth order susceptibility. And if you are not very familiar with this, so let me tell you the first order. So this is you calculate the dielectric susceptibility, and the first order the signal and the third order signal is at least I think 10 to the power 3 times smaller than the first order. And the fifth order signal will be equally that small. So so you are trying to find out a very small change on the top of a very big background, and that's why they need to do a very special set of experimental technique to figure out some amount of, let's say, some reliable signal.
Can I ask a historical question?
I do not know much about this history. Yes.
This experiment by Madan and Signager, it was Madan's thesis,
okay,
where they looked at the frequency-dependent susceptibility and picked up some signal in pi double prime. Has that just dropped out of the field completely? People have
I will come to that.
Okay.
But so we did something,
okay.
and then I actually discussed with Narayanan,
okay.
and he said that if you asked me 10 years ago, I could have done that experiment for you. But if I want to do it now, I have to spend one. Yes. Okay. Yeah. But so basically, the basic message of this is that experimentally, this is very non-trivial, very non-trivial. So I am trying to propose something which is yet this has to be yet shown experimentally. We have some results, but let me tell you at least the computational part what I did, and tell you the philosophy of this proposal. So we proposed a new susceptibility called pinning susceptibility. So the idea is that you look at these glass forming liquids and put certain quench disorder in terms of random pins, and you see the difference in their responses. And that difference should have information. I will justify why it should have information about the underlying length scale, static length scale. So we calculated, so again for this pinning there is a very long background. I am not again going into all of those. So there are a few things which I will be just referring to it. So this is, let's say, one of this glass forming liquid where there is no quench disorder. And then these black dots, they are chosen by hand quench disorder, and I want to see the difference between these two glass forming liquid at the same temperature, density, and all other. Yes.
What is the meaning of putting this disorder?
Freeze some of the particle. Yes. So they cannot move. You don't evolve them in time. So these are we changed up to 15%. But that's very high. So you for all this analysis, you need 1 or 2% of particle, or even less. Then it's fine. You don't have to put too many. And then also there are many arguments which suggest that if you choose these random pins from the equilibrium configuration, then this is still in the equilibrium. You haven't perturbed the equilibrium yet. Though there are other works which suggest that the free energy changes and all sorts of things happen. But okay, so that's another. So all the spin particles still interact with all other guys, but they cannot move. They are basically a momentum sink. So they get kick, but they just absorb it. It is like a very massive particle in some sense. So then one calculates 2-point correlation function, which is 2-point density correlation function. So what you calculate is just look at one configuration and compare it with the later time t, and you see how much is the deviation from it. And so there are these are the quantities you can calculate mathematically. And what one sees that as you go to lower and lower temperature, so at higher temperature this correlation function q of t relaxes very rapidly. This is more of an exponential at higher temperature. As you go to lower temperature, then you so there is initial first decay, and then there is a plateau-like regime which is still relaxing. Actually, it's not complete flat regime, and then eventually it decays. So this regime is called beta relaxation regime, and then this is the final decay is alpha relaxation. And now I want to put some concentration of this pin particle. You have questions? No. So. So once you put, so here I changed the concentration from, so this is unpinned, and then there are increasing pinning concentration. And you see that as you put this concentration of this pin particle, so as you increase the concentration.
It's just a 2-point correlation.
This is 2-point correlation.
There's no spatial information.
No, not yet, yes. And then you see as you increase the pinning concentration, the relaxation time becomes larger and larger. Right? This is the curve. So there is a YOLO curve which is a bad choice, but so there is one more curve here. Okay. And then what? Then we asked. So then we calculated this kind of response or susceptibility. So how much is the change of 2-point functions if I have a small amount of pin? Okay. So you calculate this derivative and the derivative at 0 pinning. Okay. So I have to also, I will show later that this derivative indeed exists. So you can choose delta rho which are different, and then still this chi is independent of delta rho. So if I take, let's say, the 0 and 0.005, and you can calculate chi p in a finite difference. You can choose a 0 and 0.02, you will get the same number. And you can, so the difference has to be same. So this is delta q by, okay, so if you calculate this quantity, so the for small thing is, so you can so this you can calculate delta q, delta rho pin, and by changing this delta rho pin, there will be corresponding changes in delta q such that the chi p remains same. So the derivative exists. Actually, numerically you can actually show it. Okay, so let's. So now then later I will show that this chi p and its peak actually directly related to the static length scale in the system. Okay, so this is the numerical results of how this chi p looks as a function of time, and this is for two different systems. One is in 3 dimensions, the other one is in 2 dimensions. Q of t is positive always, is bounded from 1 to 0.
But why the derivative?
Delta rho, yeah, so you can have, there is one more sign change,
Yeah.
otherwise it's okay. Up to a sign, this is same. The numbers are same. No, but if you, let's say, instead of you saying that you take slower, yeah. Yeah. Okay, so delta q is always positive, yes. Okay, so I just missed that, yes. Yeah, so here you can see it. You see it's become slower and slower with any amount of change in pinning. Okay, so this is how chi p looks as a function of time. You see that it initially very small, and then it has a peak, and then again decays to 0. And this peak, this is at higher temperature. As you go to lower temperature, the peak increases and also moves to the larger and larger time. Same thing happens at 2 dimensions, so it is more or less same. Okay, so now let's analyze it. So at, okay, so there is some for other who are not very familiar with this correlation function. So in glasses, this part of the decay can be well approximated by this function called a stretched exponential function. So Q of T, for large T, it goes like minus T over, so I am writing as tau alpha, which is the, and then there is a beta. This is the stretching exponent. There will be a prefactor here, some Q naught or something. This is true only for the tail, yes. So if you want to fit this part, you need to have one more Gaussian. 1 minus Q naught T by, this is again tau 1. So this is generally square. So that fits the whole data. You can fit it from here to the whole part. Okay, as we are mostly interested in the peak, and this is at the alpha relaxation time. We also that this peak appears exactly at the alpha relaxation time. So, so now if you let's say we just look at the long time part of it, which can be approximated by this stretched exponential form. You take that, okay, and as I said that the time scale depends explicitly on the pinning concentration.
And you know that the exponent doesn't change?
Yes, that we also showed, yes. So that even if so the variation, so there is some variation, but that is very minute. So like it changes from 0.5 to 0.55 or something, even less. Tau alpha increases, so that's this. This. So if you look at for the lowest temperature, this is for as a function of tau alpha is this part, somewhere here. So tau alpha is somewhere here. So when it becomes 1 over E. Beta relaxation is different, yes. Beta relaxation has something to do with the Plateau regime. Okay, so you can take a derivative and compute that derivative at let's say t equal to tau alpha, and then you get this expression, okay? And we have shown from other works, also I will also justify why this is also true. We showed that tau alpha computed at certain pinning concentration C, so if the ratio of that with the 0 pinning concentration is a scaling function, okay? We will also show the numerical evidences for that, and so it appears with the pinning concentration times some number, which is temperature dependent number. As this is a density, then it has to be one more inverse of density. So this has to be one more volume.
But it doesn't depend on C.
Doesn't depend on C, yes, yeah. Anyway, so there are more justification for why this is okay, and then also it is true that as C goes to 0, so this will become 1, so the f of x has to go to 0, and for small x we can approximate as the f of x goes as x. It can go in the other way also, with some exponent x to the power alpha or something, but with the data it is clear that it is linear. And then if you do this approximation and put it here, then you will see that chi p is, so this beta is not temperature, beta is this beta, okay, so don't confuse with that, is directly proportional to that length scale to the power d, okay. So here there is no unknown exponent related to it. So let me just tell you one more thing. So I showed you the data for chi 4, which is different than chi p, and there is one more quantity one can calculate, which is called chi of rho. So these are the things I will come back. So this chi 4 was shown to go as this is the dynamic length scale to the power some 2 minus eta, okay. But then you never know what eta is. So even if you know chi 4 peak at okay, so peak. So there is no way to reliably find out xi d. But in this susceptibility, you see that there is no unknown exponent at least. It is directly related to that dimension d. Okay. So if you know that peak, then you take 1 over like dth root of that, and that will be your static length scale. Okay, now let's come to this justification for the scaling function. why, what are the conditions that one needs to obey to have such a scaling law. So, what we try to find out is that, so we have this peak, right? This, let's say, for take one of the example, one of the temperature. So there is a peak computed at certain pinning concentration. You can compute that at a different pinning concentration also, okay? And you can find out what is the pinning concentration where this peak becomes maximum at a given temperature. So you only change the pinning concentration and try to find out is there an optimum pinning concentration where the peak height becomes maximum, okay? So that you can find out by taking one more derivative of this and set it to 0. So you take just del of chi p with a del c and that put it to 0, and that gives you an equation which is involving only tau alpha, okay? And if this chi p, there is no particular concentration where the chi p is maximum as a function of pinning concentration, then this is 0 for all pinning concentration. Okay, so this is so what I am trying to say is this chi p for a given temperature, I want to compute at a different C, okay? And I want to find out is there a critical C or particular C where this is maximum.
And you're not looking, you've lost the time, so you're not looking at peak.
Peak, yes, this peak of this, yes. And then we want to take the derivative of this and make it 0. Up and down, yeah. Max. Okay. Start, yes. So this is the equation we are trying to find out, and so is there a C equal to C star where this is maximum. Again, I was about to write Cp, so there are too many P's. And then you get this equation, okay? And if you can show that if there is no preferred C star, that means that this is independent of pinning concentration, then this is true for all concentration. You calculate, so if somehow let's say this chi p max at different C has the same height, it doesn't change with C, then the derivative is 0. Right? And then the solution will be of this form.
So then is one then arguing that there shouldn't be a reason for this peak to, so if I keep changing the concentration of pinning, then at least within the row, small row, then there should not be a concentration beyond which this peak decreases.
Yes.
The peak cannot.
Peak remains independent of this pinning concentration. It is. Yes. Yeah, but it's not picking up heterogeneity. Yeah. So that's what I will say that once, okay. So basically the point is that, let's say the solution of this equation is this, and if there is no particular Cp, and if that means that for all pinning concentration this chi p max doesn't change, then this will be true for any concentration. Right, there's a tau alpha of C at T will be tau alpha 0T with exponential of, so this is A and B, and you can rename them. That's what I did here, right, at pinning concentration equal to 0, so this tau alpha has to be same as tau alpha 0, and then there is this B of T which I just replaced by certain correlation volume, okay. So this is what is the scaling form which I used here. So if I can show that chi p max doesn't change with pinning concentration, then I am reasonably guaranteed that this scaling function will exist. Okay, okay. Before going into this check of this consistency, okay, I should have shown that. But basically, point is that so these are the calculations of the chi p max to the power 1 by d for different dimensions, compared with the static length scale computed by other methods, conventional methods, and you see for all different models. This is in 2D, Yeah, so I should have written. So these are the two different models in 3D and this is in 2D. Okay, for all the models, you see that over this range of temperature where relaxation time changes by at least 10 to the 4 to 10 to the 5. The static length scale computed by different method and the maximum of this chi p to appropriate roots of that is same as the static length scale what we computed. Okay. So at least numerically shows that yes, our arguments are probably right. Yes, I have, yes. And okay, so consistency check. So first we have to show that this derivative exists. So if I take different delta rho pin, you still get the same chi p max. This we showed it for all the temperatures. And you see that this delta C has been changed from 0.01 to 0.04 and they are all more or less in the same place. And tau alpha and the peak position, the time at where the chi p max appears, they are the same also, because that's important because I am calculating this derivative at t equal to tau alpha to remove all other tau alpha dependence or to come to this differential equation only involving tau alpha. And so this is this chi p computed at different pinning concentration. So within let's say this error, it's more or less same. Yeah, so this we have to just buy basically.
But there is a peak, like here.
This one is, but it's not systematic. You see that it goes up and the comes down. But if you take a different model, it's all jumping around. So there is no systematic behavior. And if you compute the similar quantity, where instead of putting pins, you can, so that this has been computed before. So this is, we just change the density and look at the changes in the response function. Okay, so this is chi of phi. This has been looked at heavily in literature and also computed for also experimentally. And you do see this, that there is a huge change if you change the phi a little bit.
Phi is the pinning.
Phi is the actual packing fraction. So this is chi of phi. So where so you are at some phi 0 and then you compute q and then again you do phi 0 plus delta phi, then again compute q, so q1 and q2 and then you take the difference q2 minus q1 by delta phi, and that peak changes if you compute a different density. So then for this kind of susceptibility you won't be able to write down the same scaling function. So this was argued that this chi of phi will again go as a dynamic length scale to the power some other exponent. And this is how, at least experimentally, this was, it was tried. So people have tried to find out the dynamic length scale using this method. But so the only difficulty is that there will be always some unknown exponent. And in literature, it was already shown that this exponent can vary from 2 to 4. So whatever number you choose, and then the corresponding length scale will be arbitrarily different.
It still bothers me, like
Yes.
telling me that 0.02 the peak is at some value, 0.04 it goes up, 0.0 it comes back again. So if I ask if there is a C star at which this peak has a maximum value, there is. Right? At 0.04.
What is the error bar?
Yeah.
I don't know. If you haven't showed me the error bar, right?
Yes.
So,
No, but for let's say you calculate at 0 pinning concentration. So this is okay. So I should have shown it. It is here. It goes up, down, like this. Pinning concentration. So you compute that chi p at different C. The delta C remains same. Okay. So I will show all the data. Okay. So if you are not happy with this.
The point here
Yeah.
stress is that the error bars are equal.
Yes. This is higher order correlation function, and generally the error bars are much larger.
Within the numerical constraint, there also.
Yes. Yeah. So that's what I want to sell. Okay. So you may not agree.
no fundamental reason to say that, right? It's like,
Yeah.
why should it get some concentration of
Yeah. Why there is
small enough? At large
small.
enough, I can imagine it becomes like this.
Yeah.
Difference.
At large C becomes there is a that's a different.
So at large C there will be other if the amount of pin becomes so large, then that won't remain as a normal glasses. It will become something, some low range gas or something. It is like, yeah.
Yeah, but that's
Yeah.
but maybe there is some fundamental argument saying that at small c, there shouldn't be a non-monatonicity. There shouldn't be a characteristic C star where there should be.
Right, so if you go back a couple of last weeks, there's this getting that this one.
Yeah.
This one should be okay, but when you're using this Fx to be x.
Fx to be x, yes.
That is true only when this C is
Very small, yeah. So, yeah. So this is true only, but at least numerical data shows that this straight line actually extend up to very large concentration. And okay, so I will show that data also.
Which will be at large C, this will not be.
At very large C, it will eventually fail, yes. Okay, so this is the scaling so this is tau alpha. Okay, so we wrote psi anyway. So this is tau alpha at C divided by, okay, so this is this quantity. So log of tau alpha C T divided by tau alpha 0 T, okay. And then this is f of some C xi to the power D, okay. So this is how that for different temperature relaxation time changes as you increase spinning concentration. Then you can collapse it using the static length scale and yeah, okay, so this is within numerical accuracy again, is reasonable collapse. And this straight line is this f of x equal to x. This is plotted as a log of that because the concentration changes at small to very large. And this is for another model system where it is almost like this.
What is the range of doping for this?
Up to, yeah, I think we tried up to 15% almost. Yeah. And seems fine, at least. So there is this also experimental result, the colloid experiment which appeared in this PRL 2016, where they looked at similar quantity but in a cavity. So they have created one cavity and then there are colloid particles inside it, okay. And then you look at the relaxation time as a function of radius of this. Equivalent, yeah, but looking at dynamics only. You calculate the tau alpha, not the static overlap, and you compute again, and you see that this has similar trend as pinning, random pinning, which is probably justified, that is okay. So whether you pin randomly or you put the boundary pin, that's okay. And then the scaling seems to be, actually they use the same scaling form what we proposed. Yeah, so yeah. And again, this straight line is again this f of x equal to x. This is just to support our data.
That's what I was saying, your pinning cannot be very different from freezing a boundary.
Freezing a boundary, yeah. Okay, so now the next question is that, okay, random pins again, I was always advocating that I am proposing something which will be useful for experiment, right? But the random pins only in colloid you can do it, but not in real experiment. Like if you take glycerol or something else, some liquid, you cannot put pins. There is no way. Okay, but is there a bypass? And that's what we found out. So we showed that instead of pin, if you choose certain other small concentration of particles which are bigger in size than the other constituent particles, they effectively behave as pin. So this is some sort of soft pinning. Okay. Oh, is there something 10 years back? I missed it then. Soft pinning. Okay. So there are. So now we have a system. Then there are other particles. Then there is a small concentration of much bigger particle. Okay. And now I want to ask the same question. So I want to calculate the response of this system before and after introducing small amount of larger size particle. And if, so the hope is that as this particle will be diffusing much slowly compared to the other particle, up to this relaxation time of the parent liquid, this will remain reasonably frozen. Okay. If let's say this diffusion constant of these guys are different from the parent liquid by some factor. And we also found out that actually at lower temperature it varies by like factor of 20 to almost 50. 20% to 30%. But we also showed that it doesn't matter. You can choose a very big range, starting from 20% change to almost 50-60% change. You can still compute the same. You compute the same number.
He's saying if you do this in experiments, you have a diffusion in this attraction.
But it's not that big. It's not that big. Yeah, it's not that
I
big.
remember when Kaufman was giving these talks, and she was not doing this kind of things.
Yeah.
That was the biggest question. So how much you're perturbing this?
Yeah. So if you have like this big of a sphere, then you will have this effective interaction which is coming from the collision of the other. Yeah, we are not in that limit yet. Okay, again the chi p, big mass doesn't work. Yeah, so that's what I'm actually, it's still a puzzle to us. Bigger diameter seems to be, and one argument was that that in the viscous regime inertia seems to be dropping out, and so that's why the diameter, which will be like related to the diffusion, will work. So we actually tried with the mass, and we yeah, it wasn't working, and then eventually we put the bigger diameter, which worked. So we put, so the chi p seems to be very similar like the pinning constant, like the actual pinning, and the extracted length scale again matches the length scale you compute by other different methods. So now we have, again we have done this scaling form, which seems to be working again. So this again, the line is f of x is equal to x, and tau alpha, and the peak where peak of the chi p, okay, chi p is in the same place. So it is actually peaking at the alpha relaxation time, and it doesn't matter if you change the concentration while computing the derivative. So the numbers are very similar. Again here, so within, again I will say this is, there are error bars, and so even if you compute chi4, you will see that the error bars are actually reasonably big. And I will assume that the chi p doesn't change with increasing concentration of larger particles. And we also check the diffusion constant of the larger particle, which are at least, if you take the ratio of this, which at very higher temperature they are almost close to factor of 2, but then as you go to lower temperature it becomes 25 almost. For different model it becomes even larger. And if you increase this particle diameter to be slightly larger, then this difference will increase even further. And this one is a static length scale as a function of t, computed from this chi of p by changing the other bigger particle diameter. We change from 0.2 to let's say 1.4. So this is so for the parent liquid the maximum diameter was 1, and this added large particle diameter is 1.2, 1.3, 1.4. So we have other data up to 1.6, which seems like the length scale is not changing with that. So it is within this small change is fine. Okay, next. So this is the attempt we are, so this is still something which one of my students was still doing, probably now he is not very happy with it. So the issue, so we have set up one dielectric experiment, and then the main problem is that the window over which one can calculate this quantities are, this is real, yeah. With the collaborator, I'm not doing myself, but he is doing. One of my students is the one who is experimentally, yeah. So this is done with one of my colleagues in TI for Hyderabad, T N Narayanan, another Narayanan. Okay. So one Narayanan said, so you should have told me 10 years before, but this Narayanan is fine. So what we did, we just calculated the dielectric frequency dependent dielectric susceptibility. We calculate epsilon prime and epsilon double prime both, and for glycerol, okay, and the window over which we can calculate is only 10 to the power 7, so order of 1 gigahertz to 1 megahertz, I think, right?
Yeah, this is what Menon and Sid achieved. It was 14 orders of magnitude.
Yeah, so yeah, that will be like if one can. So, but then you use different. But these are all like there is a commercial machine which you can just plug in and you can get. The other difficulty is that we are not able to stabilize the temperature to a reasonably long time to do the measurement at let's say very low temperature, where relaxation time is order of let's say minute. Then your temperature has to be stabilized at least half an hour so that you can do multiple sweep to get a reasonable smooth data. This is inverse of frequency, I think. Yeah, so I just do 1 over omega, so like some sort of time scale. And so there are these two data points. One is the symbols and the other one is the line. The lines are with, so the symbols are for pure glycerol, and then the lines are with glycerol plus some amount of sorbitol. Here it is, how much is the percentage? 3.5%. Okay. We did it for 2.5%, 5%, 10%. We also have some result with glycerol plus sugar, right? There was some sugar also. So now we computed the difference of this, or the derivative of this is the epsilon prime, which is the storage modulus.
Still small, the smaller concentration. Still small.
Very small.
Approximation you use.
Yeah, this is much small. Yeah. So this is okay. So if you convert it, yeah, the peaks are reasonably.
Given concentration.
Yeah, as a function of temperature. So basically, you just take the difference of this dotted. This is the symbol and the line, and then the peak increases. But the increase is not very large, which is I'm not very happy with this. But also this glycerol is on the somewhat is not very fragile liquid. It was somewhat a stronger liquid. So we tried to do it again with what was the other, toluene, right? Propylene carbonate. But as I said, there are like experimental difficulty, which seems to be going nowhere. Anyway, but at least there is some hope that if somebody can do it better than us, then maybe one will be able to compute the length scale.
You get time scale.
Yeah, so this is at time scale now. So this is plotted as a function of 1 over omega or 1 over f, or 2 pi by f, and again, so this is some sort of time scale.
Does the time scale correspond to some material?
Yes. Yeah. So that if you, so chi epsilon double prime is like this. Epsilon double prime as a function of log t looks like this. And this is the tau alpha, and it appears the same tau alpha, yes. It is speaking of something, yeah. So that's, so if you also.
This is epsilon double prime, right?
This is epsilon prime. Epsilon double prime looks like this.
Yeah, right. So what is this?
This is epsilon prime derivative of that.
Oh, I see.
That's a susceptibility.
This is epsilon prime.
This is epsilon prime, yes.
That's that between epsilon prime and double prime.
Yeah.
This is not epsilon double prime.
No, this is epsilon prime, yeah.
Prime, which
Derivative of
has
epsilon prime.
seems to pick up a peak at the tau alpha.
Tau alpha, yeah. And that change increases, looks like it systematically increases. And we replace sorbitol with glucose, and you get almost same again within error bar. So some data will be slightly higher, some will be lower, but within that window. So what we are hoping that if somehow we can have a bigger range and different liquids.
So sorry. So that's
Yes.
saying something interesting, right? Because the epsilon double prime will always have a peak at tau alpha.
Yes.
So the derivative of the first epsilon prime with respect to C is somehow related to epsilon double prime of your unperturbed system.
Will be, yes, of course.
But that's not trivial, right? Why should it be?
No, but again, same way, IP also has a peak like I4. But how they are related, that nobody knows.
No, but if you are seeing it, that's saying there is some underlying reason why there's a relationship between that the derivative of epsilon prime with respect to C, if I
Yes,
think of it as a perturbation, with the epsilon double prime at C equal to 0.
Yeah, will be, of course.
Why?
So again, epsilon double prime will have the same length scale appearing somewhere. But then this peak, and how it is related to the length scale is not clear. You remember chi4 also has the same thing.
There is some Kramer-Kronig kind of relationship.
So that between epsilon prime and epsilon double
I
prime,
understand.
not with after taking derivative.
But you are telling me there is, because the peak is at the same time.
It is
Yeah.
of this.
And I'm wondering if there is there's an equivalent reflection in this whole frequency dependent at C equal to 0. And that's
That one can-
measured
yeah.
impedance, right? So,
I mean, one could have asked the same question for the Phoenix sensitivity. Why
Yeah.
the time at which this peaks,
Appears exactly at tau alpha, yeah.
same as the alpha reduction.
Yeah.
which is saying something about epsilon double prime in your
Unperturbed system, yes, yes. Yeah, if we can connect it, then like that's it. We have understood something.
But I'm also saying then you have the whole.
Then this can be calculated much easily, yeah. Yeah, and there is data for over 14 decades. So you just need to connect chi p versus epsilon double prime. If that's possible, then that's it.
I just looked at it,
16 decades, yeah. So, but I think so Narayan and Menon was able to achieve much better temperature stabilization. So that's why he was able to go to much higher
Yeah, we
in.
can come back to that. But the non-trivial thing there was a very interesting dependence on frequency.
Ah, okay.
So there was a different formula for frequency.
Yeah, this was multifractal scaling, all of that.
Ah. Yeah, I should look at it. I am not. Okay. So there are recently also Ajay Sood and Rajesh Ganapati did and this appeared in this Nature.com. So in their colloidal data, and they also found out there are particles which are softly pinned, and one can compute static and the dynamic correlation and look at how they decay to find out the static length scale. Again, this is. Yeah, within I think this experimental thing, it was somewhat noisy, but still it picks up something. And we are repeating now that for our model system in computers, and for the perfectly pinned, the random pin cases, you indeed pick up the same length scale via this similar protocol. And also if you do soft pinning, again you do the same thing. Like the larger particle which are stationary over a certain time scale. Basically, it says that there is indeed something interesting happening with this chi p. Okay, so there are a lot of objections that how do you guarantee that the peak of chi p is related to static length scale, not the dynamic length scale. And our own, so at least our justification was that it is coming from this tau alpha, and tau alpha is connected to static length scale. So then it has to be connected to the static, not the dynamic length scale. But I guess, yeah, we need, but this set of data where you look at those softly pinned particle or the large particle and try to compute the static correlation around it, and you indeed picks up the same length scale, suggests that chi p indeed picks up static length scale. Okay, I have another 15-20 minutes, or I can go up to here. Okay. But with question it can go to 12:30. Okay, so anyway, just skip this part, the conclusions we know. So now let's come to another, so this is a second story which Chandan is also involved with his work. So now we are looking at a set of glass forming liquids where there are explicit crystalline order. And this is in 2D, this is the picture I showed, that you see that these red regions, they are crystal patches. So they are hexagonal, like they are in a triangular lattice. And what we asked whether this kind of glasses, so their typical dynamical features are all same as other glass forming liquids. At the same time you see that there are other glass forming liquids where you don't see any such crystal patches. So whether these two are different or they are same, is there a better understanding of these models? Okay. So recently there is this work by Hajime Tanaka, and yeah, so both of this is from Tanaka, and this appeared also in the PNS. So they showed that so this if you can compute the dynamic length scale and this length scale, which for the two-dimensional case is a hexatic order, so hexatic length scale, so they are same, and and the point to set or the static length scales are very different. Okay, so dynamic length scale and hexatic length scale. Hexatic length scale is the typical size of these patches, they are same. But if you calculate the usual method of point to set and all other methods which I discussed, so that's the static length scale, that doesn't grow much. So it's decoupled. And the question, the point is that for this kind of system where there are explicit crystal patches, that indeed is a static length scale. Hexatic length scale is a static length scale. So the point to set method fails basically. And so the big argument of point to set was that it doesn't care about what is the underlying order, it will pick up the correct static length scale. But they showed that at least for this kind of model where there are explicit hexatic order, point to set fails. And we were also somewhat, okay, so let me quickly tell you what is point to set because some of you may not know. So what you would do is that you let's say take one configuration and then you define a region, spherical region, and outside the region you freeze all the other particles. So only allow particle inside this blue region to have normal dynamics. And you ask the question whether this region will be able to equilibrate itself. So assume that if this spherical region or in this circular region is smaller in size, then it won't be able to equilibrate itself. It will remain in its initial state. But if this region is much bigger like this, then it should be able to equilibrate. So that automatically tells you there is a scale. Okay? So that typical scale over which, above which this spherical region inside this cavity able to relax gives you the static length scale. Okay, so that's the idea of point to set, and you compute different static correlation functions. Let's not go into detail. So basically you compute correlation function as a function of size of this cavity, and you see that it decays and you fit it with different functional form and it can calculate the static length scale. This is the point to set method. And as it is clear from this that it doesn't matter whether there is a crystal patch or any other patch, right? If there is no obvious order also, the system will pick up something irrespective of what the model is. But then this data says if you take a system where there are explicit crystal patches and you use this method, it won't be able to pick up that crystal patches. It should have. That's the obvious order in the system, and this data is from the point to set method and it fails. So this became some sort of issue because point to set method has been used extensively in glass literature to find out different static correlation and connections to other things. So then we picked up this and we computed all the length scale one can calculate using different methods. Again, for this system, yes. And so we have computed the dynamic length scale using 4-point susceptibility. Again, for that we can discuss separately how to do it. We can compute 4-point structure factor. We did scaling analysis, all sorts of things. So this is what the different scaling analysis, and from this you can compute the length scale. And okay, so this is how one can calculate the hexatic correlation. So what so these are all this, you compute the hexatic order, which is this psi 6, e to the power I j, 6 theta I m, I and m, the two different particle, and what is the angle between them. And if it is perfectly hexagonal, then this will become 1. Okay, so this coloring is done according to this. This is that the red is between 0.8 to 1. And then you compute, once you calculate psi 6 for each particle, then you compute the psi 6 correlation in space. Then then the peak, then you see that it decays with this kind of a power law, or exponentially, not power law, sorry, exponentially, and then you fit it and you can get the hexatic length scale. And we computed all the length scale. You see that there are at least 1, 2, 3, 4, 5, 6, 7, 8 different ways to compute different scales. And so this includes both dynamic and some of them are static length scale. All of them are in the same place. This is for the MRCO system. So the model we tried is a binary model, binary system, where so the larger particle forms these crystal patches, small crystal patches. But also to mention that this doesn't actually grow with time. So if you keep this and run the dynamics for a very long time, it's not that all the raid will come and coalesce at one place and phase separate. That doesn't happen. So it is not phase separating at all. For this model, now we see all the dynamic and static length scale are same. This includes point to set also. So that means what Tanaka got and what we are getting are different. In our model system, which is a binary, where we computed, we have there is explicit MRCO, but when you use point to set, it picks up correctly the hexatic order. We are somewhat, if you do it for other model where there is no explicit order, then you again repeat the same thing, and you see that this is the dynamic length scale and this is the static length scale. So by the way, this is the hexatic length scale which doesn't grow. And you see there is a very large decoupling between static and dynamic length scale. Then what we said, okay, let's look at variation over density, because they vary density. So maybe the density is what is one of the, so temperature and density probably not equivalent.
So in the systems with the medium range with hexatic order, you're saying the dynamical and the static length scales fall on top of each other.
Yes.
Because there is some growing order, they are related.
And even if you compute it with point to set, it is same.
No, that controversy I'm not getting. That's not, I was just asking that there's this interesting difference between systems which have a hexatic order and not, is that in the ones with hexatic order, the dynamical and the static length scales
are
fall
same.
on top of each other.
On top of each other, yes.
But if you don't have a hexatic order growing, then those two are different.
Those two are different, yes. That's what. So then we looked at another model where we vary the density, and you again have this medium range order in the system, and you indeed see, even with changing density, both the static and the dynamic length scales are connected. They are same. And okay, so these are all different ways to check whether they are indeed correct. Instead of looking at number, you do a cross plot. You see, so this is tau alpha, which is controlled by the static length scale. This is Binder cumulant of this overlap correlation function, and this is controlled by the dynamic length scale. So you do a cross plot of that. If you get a master curve or the data is on top of each other close by, then both the static and dynamic length scales are same. And for this model, which is this 2D R10, where there is no explicit crystal patches, you see that you cannot have this kind of nice collapse. So then we moved back and looked at exactly the same model with Tanaka looked at. So this is a polydisperse model, and we repeated the same analysis, and we computed.
So it's not bidisperse.
It's polydisperse now, and we computed. So these are all different dynamic length scale. So this is the black dots, black spheres are hexatic order length scale, and then you do tau alpha scaling, that should pick up the static length scale, and it indeed picks up static length scale. Then do S4, which calculates dynamic length scale, again it picks up the same. Then you can compute point to set, the point to set is here. So it was surprising that, okay, so polydispersity is what is important. Okay, where this thing seems to be failing. It was not clear why even with polydispersity it will fail. Then we tried to look at, let's say, distribution of density and polydispersity inside these cavities while computing point to set. And we found that there is a very large variation. And the width of this, so this is the mean, the bulk density, and this is the variation. And one needs to do very large averaging over number of cavities. So it goes up to more than 250. So beyond that, we were not able to do it because it was already hitting all the box size. And then what we said that, okay, so this variation seems to be playing a big role. And the point to set method has one argument, that the bulk and the cavities should have same thermodynamic state. So density and polydispersity has to be same. We said, okay, now look at only cavities, those are close to this bulk limit. And then you compute again. And then you indeed say that so this data points, so this ones, the magenta. So now they come back to the same length scale. So if you can compute the point to set in an appropriate way, making sure that the cavity has the same thermodynamic parameters, then it will indeed pick up. So it is still order agonistic. Okay. And so then so this was mostly done on two-dimensional systems. Then we tried to see, is this true even for 3D systems? And at least we have one model, which is this 3D, this is not Cobb-Anderson type, this is slightly different, some 82 versus something. So there are details of this BMLJ _82, okay. So, so the parameters are different, but it is still a Lennard-Jones interaction. And there one sees that static and dynamic length scales are same, and the origin seems to be related to locally favored structure, which is called LFS. Again, so this goes into another detailed discussions. In 3D, there are tendency for certain structural motifs to grow, and if you have a systems with that structural motifs, and if they can grow, then both static and dynamic length scale will be the same as the size of those motifs. Okay, and so this is the work by Patrick Royal and Gilles and this guy Turchi, and so what they have looked at, they have a three-dimensional system, and so this model icosahedra seems to have is some sort of a structural motif which is favored energetically, but in a flat space they are frustrated, so they cannot grow. So what they did, they now looked at the dynamics of this in a curved space. So with increasing curvature, the frustrations for icosahedra to grow to a bigger scale decreases. At some point it vanishes, and so this is increasing curvature of the space. This is Euclidean, and then you go into certain amount of curvature, and then there is a very sharp change, and the system actually crystallizes to icosahedral crystal motifs. And during this process, again the static and dynamic length scale become same. So as you go to larger curvature in space, then the icosahedra grows bigger, and static and dynamic length scale become same. So this is exactly what is similar to what we are seeing basically. And so the one interesting point is that there are many experiments which suggest that metallic glasses has these structural motifs which seems to be growing. And the questions we should understand or ask is that whether metallic glasses belongs to this kind of models. Okay. So let's not go into that. So the whole point is that if there are structural motifs which has a tendency to grow, it need not crystallize. As a tendency to grow, then the static and dynamic length scale will couple strongly. If not, then they are decoupled. So we have at least within this temperature window or density range, two types of glasses.
But still at the glass transition, there's nothing dramatic happening.
No, it's okay. Yeah, I am not concerned about. Yeah,
Just ask.
yeah. So the only point is that if let's say for these models where there are structural motifs, maybe physics.
Length scale grows.
Yeah, or the physics may be simpler. Let's say there is one scale which controls everything.
But do the length scales grow more if there is a static?
Doesn't look like. At least for, again, if you look at, the changes are the same for 4 or 5, it is not huge. Yeah, it will be good to have a model even with these structural motifs where the length scale grows by, let's say, a factor of 100. Then it will be great. But we haven't, there is nothing like this yet. Okay. Yeah, so there are other controversies also, I'm not going into this. But if you are interested, look at the paper which appeared this year in PRL, and there is a very big supplementary material. So read the supplementary, not the main paper. Okay. Okay. So let's acknowledge the collaborators. The first part, the theory simulation was done by my student and Soris, who was a postdoc with Chandan. An experiment, Vanu tried his hand, and this is T.N. Narayanan, my colleague, and this is his postdoc. So these 3 people, I also did one measurement at least. So
Yeah, in the lab.
Yeah.
And nothing.
Yeah. Oh.
That's the problem.
Okay, and the second part was done by Indrajit, and so with Siladitya, Srikanth and Chandan. So we all participated and made it happen. And thanks for your attention. Connection between static and dynamics here, but I think it should be one time.
So we've been looking at studying this in the context of activity, but forget about this hard process on that. There, the order seems to be growing quite a bit. You can identify a sublattice order. It's not hexatic or anything, but you can identify the static length scale.
Yeah.
Seems to be growing quite a bit. So
okay, maybe
I have not been focusing on it, but something interesting.
So that model may be the best one to look at maybe. And
It doesn't order.
Then it would, but through a first order transition. So the supercooled stays.
Yeah, at least there is a supercooled regime where things seems to be. Yeah. No, even say like in 3D, there are model system which Sarika looked at, or you just vary different parameters and compositions also, and there is a tendency to crystallize, but not a global crystal. So those models probably also will be useful to look at.
Yeah, there's a tendency to crystallize.
Yeah.
But it's a first order transition.
First order, yeah.
So you can create.
Yeah, you can have at least look at some of this. But I think the next, what I would like to look at is the metallic glasses with this some embedded atom model or something. You want to
Effective medium. Sorry, embedded atom.
embedded atom, yeah. And want to see whether, because there are many experiments which was done and all of them seems to be suggesting that there are crystal, nanocrystals of certain motifs. So, anyway.
There might not be frustration. So in the hard process, interestingly, it's frustrating. So there is.
Yeah, single component in 3D. Yeah, so single component in 3D may not be a bad idea. We have done it for the 2D. So there are other controversies like hexatic phase transition happens, and so that's the slide I skipped. That was one of the.
But I think you guys should go back and look at this frequency dependence assessment. There is something there.
Okay.
That,
Yeah.
You know, again, it's like the field moves on. Right? No one answered the question.
And it. Yeah. Yeah. No, I think.
The fact that you are seeing this, I think there might be something.
Some relation between these two. Yeah, very likely.